The accounting method is a method of amortized analysis that is inspired obviously by accounting. So what we're going to do is we're going to, in the accounting method, we're going to increase the cost of some operations in order to get credit for others. What does this mean? Okay, so we have the stack example that we used where we have a push and we have a pop and we have a multi-pop. And we're going to have a cost for each of those. So the cost for push is 1, the cost for pop is 1, and the cost for multi-pop we decided was the minimum of the number of pops and the total size of the stack. Now what if we create something called amortized cost, and we're just going to pretend that push costs 2. So say $2. Pop is free and multi-pop is free. And what we're going to do is, now push really, its actual cost is only 1, but we're going to say it really costs 2, and we're going to take that extra dollar and we're going to store it and save it up to use later on the pops and multi-pops. So here's some intuition you can think about. So the classic example of a stack is with plates. We have a plate and we push it on the stack. Well, when we push that plate onto the stack, what do you say we put $1 on it? So we pay $1 to push the plate, and then we put the other dollar of the cost of 2 onto the plate. Then we're going to push another plate. So we have 2 plates, and we're going to put another dollar on that plate there. So now we have $2 stored up. And we do that iteratively, or recursively, I guess. So we have n plates, and we have $1 on each plate, so we have n dollars stored up. Then, when I do a pop, instead of using the cost of the pop, we're going to use that dollar to pay for the pop. And since multi-pops just use pop under the hood, we get to use those dollars. And so, we can say that pop and multi-pop are free because we've saved up money for it, to pay for it. Okay, so if we have n pushes and we add on to that n pops, then what is the cost? Well, we said that push is going to cost $2 for each, so the cost is 2n for the pushes plus 0 for the pops, and that is 2n equals order n dollars. And so on average, any operation is going to be order n divided by n. Any operation after n operations, and that's constant time. So a push or a pop or even a multi-pop is on average going to have a cost of a constant number. Okay, so we might ask ourselves, well, how can we prove that? Is that going to work every time for whatever amortized cost we choose to use? Could we say push is going to cost $1 and pop and multi-pop cost 0? Well, for this to work, we have to say that the sum over n operations of the amortized cost, which we're going to call C hat, so amortized cost. Now the amortized cost, remember, is the cost we constructed, so where push costs $2 and pop is free. That has to be greater than or equal to the actual cost. So what we're doing here is we're saying that the amortized cost is an upper bound of actual cost, right? We said it's greater than or equal to. And this is what we must show for the accounting method. Okay, so let's do it for the stack case. So for the stack, the amortized cost over n operations is $2 times n. So that's equal to 2n. And we want to show that that is greater than or equal to the actual cost. So the actual cost is the sum over n of the cost of a push, which is one operation, plus the sum over n operations of a pop, which is equal to 2n. So we can check that off. Let's do our binary counter example. And let's use the following amortized cost. Set a bit to 1, we're going to charge $2. And to set it to 0, we're going to say it's free. And so if we look at the algorithm, so this is again on page 454. We see that if we use these costs, this right here is free. So the only cost to increment is setting it to 1. So the total cost, so the whole loop is free. And so incrementing n times costs 2 times n, which is the cost of setting a bit to 1, which is the cost of a single increment, right? That's the only cost right there. And that is order n. Now, I said that the loop is free. That's not entirely true. We have the cost of looking at the comparison here, but we can easily take care of that by incrementing our cost of setting a bit to 1. We could set it to 3, and it would still be linear time.